Swayam Prabha. Digital India. Educated India.
In my previous lectures, I have discussed about the liquefaction susceptibility criteria for coarse grain soil and fine grain soil. So, now the one thing I want to discuss related to these two criteria, that I have discussed that if the coarse grain soil, whether the coarse grain soil will liquefy or not, and how to will check the liquefaction susceptibility criteria for fine grain soil. Now, by definition, the coarse grain soil means the amount of fines is less than 50%. Okay, and for fine grain soil, by definition, the amount of fines is more than 50%. So now the criteria are given for fine grain soil, that if the plastic limit is less than 7, then it is a sand like material, it will liquefy, and if the plastic limit is more than 7, then it is clay like material, means slightly softening, or if the plastic limit less than equal to 7. Okay. So now the in case of coarse grain soil, I have discussed how to check whether the liquefaction will occur or not, and there I have solved one example problem, and in CPT also I have discussed then how to check the type of soil. Okay. So there it is mentioned that if it is clay, then you use the either you use the Chinese criteria to confirm that liquefaction will not occur, or it is too clay rich that to liquefy. So now or you can do the test to confirm that the type of soil and the liquefaction possibility is not there. So that is one option. Another is that if it is sealed, then also the same technique you have to use. So that means it is given for fine grain soil, either you use the Chinese criteria or you do some test to confirm that the liquefaction will occur or not. Or and if it is the amount of fines is less than 15% as per Chinese criteria, then liquefaction will occur. But from when I discuss about that fine grain soil susceptibility criteria for liquefaction, there I have discussed that the Chinese criteria now, in addition to Chinese criteria, you have to use other criteria also, and that's why I have given few other criteria to show for the fine grain soil liquefaction will occur or cyclic mobility will occur. Now there is a question that even in the coarse grain soil, there is a possibility that if there is a fines are present, now there can be a possibility even in the coarse grain soil also the PI value can be greater than 7. Yeah, there is a possibility that even in coarse grain soil also PI value can be greater than 7. Now the question is that in such case, can I use that fine grain liquefaction susceptibility criteria here, that if it is PI value is greater than 7, then it is a cyclic mobility, cyclic softening. But there is no such confirmation that those fine grain criteria can be applicable here. So that means fine grain criteria are applicable if the amount of fines by definitions are greater than 50%. That means the fine grain soil. But in the coarse grain soil, because of the presence of fines, if the PI value is greater than 7, then there is no guarantee that the fine grain soil criteria will work here. Okay. So, and if it is less than 7, then definitely it will be sand like material. Even the fine grain liquefaction susceptibility criteria also says that. So that means in such case, it is recommended that in addition to the Chinese criteria, you do some further test, laboratory test, to confirm that the liquefaction will occur or not. Clear? So that means the fine grain soil, the criteria is clear cut. In the coarse grain soil, for if it is even if there is no fines or less than 5% fines or 15% fines, then liquefaction will occur definitely. Possibility of liquefaction is there, and you have to check. And but if for coarse grain soil, because of the presence of fines, the PI value is greater than 7, then it is recommended you check, do some further test and see whether liquefaction will occur or not. Okay, and by definition, liquefaction I have given the first slide definition when I started my liquefaction career. So still I am giving that definition, and whether cyclic mobility or the flow liquefaction, both are termed as liquefaction, and then we have to follow this criteria. Okay, that is one thing. Another one, that when I solve the my first my example problem, I showed how to take care the footing load or foundation load to check whether liquefaction will occur or not. There I consider on isolated footing, and that can be wrapped also. You can check it for the wrapped also. So in the wrapped, then your influence zone will be more. And in that example problem, I took up to say 10 or 12 meter. If your dimension of the wrap is 10 meter by 10 meter, then up to 10 meter the factor of safety will be same that you will get for wrap factor of safety. Beyond the 10 meter, the factor of safety will increase. That the same thing that I followed in my isolated footing, that up to 4 meter the factor of safety is same. Of that influence zone, that here the width of the foundation was 2.5 meter. Then the factor of safety increases, and the your factor of safety for static factor of safety, and then the seismic factor of safety increases, and the liquefaction factor of safety will also increase. Okay, and then a similar way you can do it for the slope also. Okay, similar way you can do it for the slope to calculate the K alpha value to determine you can do the slope stability analysis, and you can find how much static shear stress is present in that slope. Okay, what I did for that soil under footing load. Now here when I did the liquefaction susceptibility checking for clay, I use that your tau cyclic divided by SU into n equal to 30. Okay, so why that 30? 30 means is magnitude of earthquake 7.5. I told you in my previous lecture that for the clay, the equivalent number of cycle is for if I take 65% as maximum shear stress as the average shear stress, then it is the equivalent number of cycle for clay is around 2 times more than the equivalent number of cycle for sand, that I showed. So here for the sand, for magnitude 7.5, the equivalent number of cycle is 15. So here 30 for is the clay, that is the equivalent number of uniform stress cycle. Clear? So these are the information that I want to give you. And now I will start today's topic, the settlement of sand due to earthquake shaking. And before I start this topic, I will discuss the another topic, which is the cyclic, your liquefaction susceptibility criteria that we have discussed till now is cyclic stress approach. That means we have discussed the one is the shear stress required to cause the liquefaction and the shear stress developed during an earthquake. So that means stress was involved. So that is called cyclic stress approach. Now similarly, cyclic strain approach is also there. Here we will determine the strain required to cause liquefaction and the strain developed during an earthquake, and then we will compare. Okay, so how to do that? So first we will calculate the amount of strain that will develop during an earthquake. So how we will calculate that? The amplitude of uniform cyclic strain can be estimated from the amplitude of the uniform stress cycle as. This is the same almost similar expression for the shear stress developed during an earthquake. So here we are actually calculating the shear strain developed during an earthquake. So this is cyclic strain. So which is also 0.65 gamma A max by G, then sigma V R D, now divided by G, because previously it was stress, now we are dividing it by shear modulus, then you will get the shear strain. So this way I will get the shear strain. Now where, remember that here the shear modulus is function of the shear strain, because you know that shear modulus is not constant, G max is constant, but G shear modulus is not constant, it is a function of strain or time or number of cycle. So it is a function of strain. So that's why because if you know the shear modulus, then only you can determine the cyclic strain, but shear modulus also is a function of cyclic strain. So it is an iterative process. So that means how to calculate the cyclic strain that will develop during an earthquake, that where shear modulus is G is the shear modulus of the soil at shear strain equal to that cyclic shear strain. Shear modulus can be estimated from the G max and appropriate modulus reduction curve. So I have discussed about the modulus reduction curve. So this is your modulus reduction curve. So G by G max curve. Okay. So you for that particular soil first developed or produced this shear modulus reduction curve that you can generate. Now from here by iterative process you can calculate the shear strain. That means if you know the G max, then first you assume one particular strain or first you assume one G. Okay. So first you assume one G and then you check that the strain that you are getting and your assumed shear modulus are close or within the your tolerance value or not. Then otherwise you go for next trial, and then this way you can calculate the shear modulus that will develop during an earthquake. So first you have to generate this shear modulus degradation curve or shear modulus reduction curve, then you should know the G value, then from there you should know the G max value, and I have already discussed how to determine the G max, all these things. Then you can determine the G, but remember that your G is the function of strain. Okay. So that means here you need the G by G max curve with strain, and damping ratio curve is also another thing that is required for your for this equivalent linear analysis. So you know, but here damping ratio curve is not required, only if you have the shear modulus degradation curve, then that is enough. Now once you get this cyclic strain, so then another few things are required, that is your the equivalent number of strain depends on the magnitude of earthquake. Okay. So that means here equivalent number of cycle, that will also depends on the magnitude of earthquake, that determines cyclic strain, the cyclic strain that will determine, that means the strain that will develop during an earthquake will be compared with threshold strain. First preliminary will compare it with the threshold strain, and which can be estimated as by this equation, where E is the elastic modulus in PSI. Okay. This is pound per square inch, that is PSI, and mu is the Poisson ratio of the soil. F can be taken as 0.5, sigma is the total normal stress, which is also PSI, and considering the particular practical confining pressure range, the threshold strain value could be in the range of 0.1% to 0.04%. But you can calculate for your own soil if you know the elastic modulus, Poisson ratio, and normal stress. The stress at the depth at which you are checking that threshold strain, then that's where you can calculate the normal stress, if you know the your unit weight of the soil. So you can calculate the strain T or threshold strain. Now you compare this threshold strain, but the strain range is threshold strain range is 0.1% to 0.04%. Now if the strain cyclic strain, that means developed cyclic strain is less than the threshold strain, then the liquefaction cannot be initiated, at pore pressure will not generate. But if the cyclic strain, developed strain is greater than the threshold strain, then the liquefaction possibility is there. Liquefaction possibility is there. So, you have to check it. Now, how will check? Then we know that in my previous cyclic stress approach, we determine the cyclic stress developed during an earthquake and the resistance stress or stress required to cause the liquefaction. So, here also, here we have developed the strain, we have now we know the how much strain is developed during earthquake, this is the expression. Then we compare it with the threshold value. If your developed strain is greater than the threshold, then you have to check it because the liquefaction possibility is there. How will check? So, this is the expression by which we can determine the strain required to cause the liquefaction. So, that to evaluate the liquefaction resistance of the soil, the amplitude of a series of uniform number of equivalent strain cycle is compared with the cyclic strain amplitude required to initiate the liquefaction in the same number of cycles. Okay. So, that means first you have to decide that under which magnitude of earthquake you are designing your or checking the liquefaction possibility. Now, from there you can calculate what for that corresponding to that magnitude of earthquake, what would be the equivalent number of stress cycle, okay, or equivalent number of strain cycle. Okay. So, now with that same equivalent number of strain cycle, you check how much strain will be required to cause the liquefaction. Okay. So, that is saying here that will be compared with this strain cyclic strain amplitude required to initiate the liquefaction in the same number of cycles. That means the same number of cycles or same magnitude of earthquake. Now, cyclic strain amplitude required to initiate liquefaction in the NEQ uniform cycle can be expressed as by this equation, where RU is the pore water pressure ratio that I have already discussed, the pore water pressure ratio to initiate liquefaction, or threshold pore water pressure ratio. Alpha and beta can be experimentally determined and are function of Kc. What is Kc? Kc is the basically ratio of vertical effective stress to the lateral effective stress at a point. That you can calculate. Okay, if you know the sigma V, then you can calculate the sigma H also in the function, or you know the sigma H dash is K0, Kv dash into K0, you can calculate by 1 minus sin phi. So, that you can calculate, and beta and alpha can be expressed in terms of Kc also. What is the expression of alpha? Alpha expression is 4.78 minus 1.91 Kc, and beta is equal to 2.96 minus 0.78 Kc. So, first you calculate the Kc. Now, use that Kc for that particular depth, then use that Kc to calculate alpha and beta. Now, that you put in this equation. So, in this equation, what are the unknowns? Alpha is unknown, beta is unknown. NEQ you can calculate if you are designing for a magnitude of earthquake, say 7.5, then you know the equivalent stress cycle is 15. Similarly, you know for the sand that what would be the equivalent stress cycle or stress for a particular earthquake. So, and then now the how you calculate the RUT. So, RUT you can calculate, there is a Kc range is also given, but you can calculate the Kc for your own. It varies from 1 to Kf, that means K is the failure. So, general range that is used for this study is 1.22 to 2.25. So, now Ru you can calculate by this equation. Ru is equal to Ut, that means the developed pore water pressure divided by sigma 3 dash. So, that is for triaxial I have discussed, and for field Ru is sigma Ut divided by sigma V0 dash or sigma V dash. Now, this is the expression of RUT. So, here also Kc you know tan 23 degrees. So, you can calculate the Kc. So, from the Kc you can calculate the Ru, from the Kc you can calculate the alpha, from the Kc you can calculate the beta also. So, now you know the Ru, now you know the alpha, now you know beta, you can calculate the cyclic shear strain required to cause the liquefaction. Now you compare it with the strain developed during an earthquake. So, cyclic strain is the strain developed during an earthquake, and this is cyclic strain T means the threshold strain, and that means the strain required to cause the liquefaction. So, if your developed is cyclic strain is more than the threshold strain, then the liquefaction will occur. Okay. And so that means the first you calculate the cyclic strain developed during an earthquake, then preliminary check with the threshold strain. If the developed cyclic strain is less than threshold strain, then possibility liquefaction is not there. If it is greater than that, then there is a possibility, then you have to determine the strain required to cause the liquefaction. Then you finally check it and just see the liquefaction will occur or not. Okay. So, now what are the few points? So, few points are the cyclic strain approach is derived from the relationship between the pore water pressure generation and cyclic strain amplitude. So, that is why pore water pressure can be predicted more accurately from cyclic strain approach as compared to the cyclic stress. Okay. So, but the accurate prediction of cyclic strain is more difficult than the cyclic stress. So, that is why cyclic strain is not this approach is not most commonly used. So, generally cyclic stress approach is most commonly used. So, now I will go to the today's topic, that is settlement of sand due to earthquake shaking. So, I will discuss it for two cases, first for dry sand and then I will discuss it for your saturated sand, okay, when it is subjected to earthquake shaking. So, for the dry sand, first what I will calculate the strain effective. Okay, I will calculate that. So, this is the average shear stress, that means stress developed during an earthquake divided by G effective. Okay. So, that means this is my basically the strain effective is the stress divided by G effective. So, now that I can write that the average stress divided by G max into G effective divided by G max, that I can do, and from here I can write that strain effective into G effective divided by G max, that is equal to tau AV, average shear stress developed during an earthquake, divided by G max, where G max is the shear stress, shear modulus at low strain level. Okay, and G effective is the effective shear modulus at induced shear stress, or sorry, shear strain or that is because here G is function of shear strain. So, that is the effective shear modulus at induced shear strain. That means the effective or shear modulus at that induced strain, because your shear modulus is also function of strain, remember that. G max is constant, but not the shear modulus G, and tau AV is the average cyclic shear stress. How I will calculate the tau average? Tau average I will calculate by using this expression. into sigma V into RD. Okay, and there is a expression. So final expression, effective strain into G effective divided by G max, that is equal to, now it is tau average divided by G max. So tau average 0.65, that is A max divided by G into sigma V RD divided by G max. So that is the expression of strain effective into G max, G effective divided by G max. Okay, so now we know this expression, how we calculate this term. Okay, so now here you can see that we have a chart. So we have a chart. From this chart, x axis is strain effective into G effective divided by G max. Okay, and y axis is the shear strain effective, and this is the chart for sigma dash m. So what is sigma dash m? That is, you know, that is your mean effective overburden pressure. Okay, so you know that sigma m dash you can calculate by sigma 1 dash plus sigma 2 dash plus sigma 3 dash. So generally that we can consider that this is sigma v dash plus 2 k0 sigma v dash, that you know. Okay, so this will be ultimately 1/3 sigma v dash 1 plus 2 k0. Okay, so that is my sigma v, sigma m dash, or sigma v dash or sigma v 0 dash, so all are same. So now if you know the for a particular depth what is sigma m dash, then you can calculate the shear strain at that point. Okay, now once you calculate the shear strain, now you have, now the two charts are given. So this procedure was developed by Tokimatsu and Seed 1987. So this is the reference, you can see this publication. So this procedure was developed Tokimatsu and Seed. So now they have provided two charts. So it is shear, cyclic shear strain divided by volumetric strain due to compaction, because when there will be a shaking in the dry sand, there will be compaction. So this, due to that compaction there will be settlement, that settlement we are measuring. So that is the volumetric strain due to compaction. So if this is the two charts for moment magnitude 7.5, it is 15 cycles you can see, and I have already discussed that for the sand the equivalent number of cycle for magnitude 7.5 is 15. So this is the two charts are given. If you have N160 value, then you can use this chart, and if you have the relative density, then you can use this chart. So right side chart is for N160. If you have available N160 is available, then you can use this chart, or if you have relative density is available, then you can use the left hand side chart. But these two charts are for valid for moment magnitude 7.5. So now if from this chart, if you know the shear strain, then corresponding to then from these two charts, either this one or this one, you can get the from the shear strain to volumetric strain. Okay. Now once you get the volumetric strain, then from there you will get the your settlement. Clear? So that I will discuss. Now here as it is only developed for your magnitude 7.5, these two charts are given for magnitude 7.5. So that's why we need a magnitude correction factor is required, because we have to apply some correction. So that for these corrections it is given that for your vertical strain, this is your volumetric strain. So, this is volumetric strain. So, for any magnitude m divided by volumetric strain for magnitude 7.5. So, that value is given for magnitude of earthquake 5 to the power 1 5.25 actually. This value is 0.4. If it is 6, this is 0.6. So, if it is 6 by 34, then it is 0.85. If it is 7.5, obviously it will be 1. And if it is 8.5, then this value is 1.25. So, that means first you calculate the volumetric strain for magnitude 7.5. Now, if your magnitude say 8.5, then you multiply that volumetric strain that you have determined for magnitude 7.5 with 1.25. Then you will get the volumetric strain for magnitude 8.5. Clear? So, in the next class, I will discuss about the steps, how you calculate this shear strain, then from shear strain to volumetric strain, and from there finally settlement. By this one by one the steps I will discuss, and then I will discuss I will solve one numerical problems also, and then I will discuss the how to calculate the settlement or determine the settlement for saturated zone. Thank you.